Section 11.7. We're going to build on something that we started talking about in the section where we talked about tree diagrams. If you remember, we were drawing pictures to list out the sample space of a certain experiment. And we came across something called the counting principle. So we're going to revisit the counting principle here in this section. Then we're going to elaborate on it a little bit, and we're going to come up with something called permutations. Okay, which is just something that is derived from the counting principle. So at the top of the sheet, if you're watching the video, you can print this sheet. It's right on Canvas. It's a PDF, or you can just open up a window and follow along. At the top of the sheet, I have revisited the counting principle. We're going to do a couple of problems to review that. So real quick, the counting principle says if a first experiment has m distinct outcomes, so one of the examples we did is we flipped a coin, so 2 outcomes, and a second experiment has n outcomes, so then we roll the die, has 6 outcomes, then when I do the 2 things together, it has m times n distinct outcomes. So in the case of flipping coin and rolling a die, 2 times 6 gave me 12. We did the tree diagram, we listed out all 12, and we had a really good time. Okay, so now we're going to use the counting principle in the same sort of way, but we're not going to do tree diagrams. So example 1, my example. Okay, so all my markers are slowly dying here. Okay, example 1 right here says this, you just got a new phone, so you're setting up your passcode for it. And so it needs to be 4 digits. And so I want to know how many different passcodes can you make? Okay, so I need to make 4-digit passcodes. I'm just going to have 4 lines right here, just representing each. Like we're going to fill in the blanks. So this is going to be a digit, a digit, a digit, a digit. So tell me, as you're thinking about your favorite passcode, how many choices of number do you, so we're making a number code. How many choices do I have for the first digit? There's 10, right? 0 through 9, there's 10 choices. We're not given any sort of limitations to what we can choose or anything like that. Times, how many, pardon me, how many choices for the second digit? Again, no limitations. Third digit, and then 4th digit. And so that is 10,000. There's 10,000 different passcodes that you could make. Okay, so that means that if somebody's going to guess, then they would need up to 10,000 different guesses in order to figure out your code. Okay, but you know, we live in an unsecure world, and so example 2 is going to be your example. It just changes the problem slightly. If you have an Apple phone, then you know a few years ago they changed it from a 4-digit code to a 6-digit code. So please tell me, I'll give you 30 or 35 seconds, how many possible passcodes are possible if now we have to pick a 6-digit code? Okay, again, no limitations were given. This is just a very straightforward counting principle. And so what you've done, hopefully, is there are 10 choices for each of the 6 digits. And so when you multiply that together, you've got a 1 with 6 zeros. So that turns out to be 1,000,000. There's 1,000,000 choices. Okay, so you can see that's why having a 6-digit code is more secure. You go from 10,000 options to guess from to 1,000,000 options to guess from. So you've increased it by a couple orders of magnitude. Okay, example 3. If you have a question, we're just revisiting the counting principle, but I know you might have been asleep that day, or maybe you didn't feel too good. So if you have a question about it, please ask whatever you need to about this, because the counting principle is going to be part of the last 2 sections that we have in this unit. So example 3 says you need to make a password for some website, because everyone wants a different password. That's why I can never remember what my password is. You need to make a password consisting of 2 lowercase letters followed by 4 digits. And so there's 3 examples here. I'm going to go ahead and do the first one, then I'm going to, no, actually you do the first one, and then I'll help you with the second one. How about that? So the A problem says, how many possibilities are there if repetition is permitted? Okay, so we're going to have 2 lowercase letters followed by 4 digits. I'll give you a moment to throw in some numbers and make your hypothesis on what you think the number is. Okay, so here we go. If I have to have a lowercase letter of some sort, how many options do I have for a lowercase letter? 26. Now you might be saying, why did they say lowercase? Well, because if you're in a website like some of them are, where the case matters, okay, so if it could be either upper or lowercase, what does this number become if case matters? 52, yeah, so you're increasing the number of options. So again, repetition is allowed, so that means there's 26 options for the next letter. We've already visited this thoroughly. There's 10 options for the digit. Repetition is allowed, so nothing changes. And so when I multiply all that together, 26 times 26 times 10,000, that's a lot. So it's 6,760,000. Any struggle with where these numbers are coming from? What's going on? Please ask me. I want this to be a nice, relaxing walk in the park today. Well, I mean, that seems like a lot, but you know, people are very good at using computers to break in things, and a computer can go through 6 million things. That's why they recommend the longer code, the better, because it makes more options. So even though 6 million is a lot, your hacker friends, they can take care of that in a few minutes. Okay, so now let's say we want to do the same thing, but the website says, okay, you can't repeat anything. I don't know why that would be the option, but it just makes for a fun problem. So I've got my 2 letters and I've got my 4 digits. You're going to help me with this one, and then I'm going to give you the C problem to do. So how many options do I have for the first letter? Okay, now, if repetition is not permitted, how many options do I have for the second letter? 25, there you go. You remember, it's kind of like when I do something without replacement, as we talked about in the previous section. My first digit, I have 10 options. How many options do I have for the second digit? And then, there you go. If you can't repeat, each successive digit you choose, you have 1 fewer. Again, does anyone have a question about why a particular number is where it is? Please don't be shy. Please ask whatever you have to ask. This is basically the basic concept of the question. We're getting there. Okay. Yeah. 3,276,000. Okay, so I would like you to do the C part, please. The C part gives some even more detailed restrictions, so you can figure out how many options there are. That's a great question. I probably should have identified that What do you guys think? Let's do math by democracy. Is Y a vowel today or not?
Yes.
I always learned A, E, I, O, U, and sometimes Y, but like this word right here, by, Y is clearly a vowel, right? So I'm going Y is a vowel, okay? Just because bye. Well, that's not, that would be spelled with an E, so that anyway, so what? No, it's not case sensitive. I didn't specify, so we won't. Wasn't prepared for such complex questions first thing in the morning. All right, so here we go. This one says the first letter must be a vowel, the first digit cannot be 0, and repetition is not permitted. Okay, so we came to the conclusion a moment ago that Y is a vowel, so that means how many options do I have for the first letter? 6. Okay. So now I picked the first letter, I'm not allowed to repeat. How many options are there for the second letter? 25, great. The first digit can't be 0, so how many options do I have for the first digit? 9. I've used whatever digit that is. How many options do I have for the second digit? 9 again, because now we can use 0. We're throwing 0 back in here. So this one's 9 because the restriction was we can't have 0 for the first digit. So whatever one we pick, 3 or 7, okay, but now here 0 is allowed again. Okay, that's not a restriction, but we've got one we can't use from there. So then 8 and then 7, there we go. There's all of our thing. And did anybody do that multiplication? What's that come out to be? 680,400. Okay, so now the question was, is this kind of the gist of the lesson? Well, example 4 is going to take us to the gist of the lesson today. So you have framed pictures of 6 family members.
I'm really confused on how you did that problem. I got a really wrong answer.
Okay. So what number do you have here? 6. So we're good so far. What number do you have here? 20? Okay. So this one said vowels. Okay. And so there were 6 vowels. Was there any sort of restriction on the second letter that I could use? It did not say. So now we're back to the whole full 26 letter alphabet, except we're not allowed to repeat. So we're not going to use the letter that was used here. So if this was, let's say we pick A, now I have 25 other options that I can pick right here. Okay, so that's why it's not 20. The options here aren't everything but vowels. Okay. That could be something I could have spelled out, but I did not give any restriction at all on the second letter. Is that the one? Are we good the rest of this?
And then I put 9876. Like, because I was confused on like the 0 and stuff.
Okay, right. So this one, the choices are, because we're not allowed to use 0, the choices are 1 through 9, right?
Yes.
This one, there was no restriction, so you could use 0 through 9, but repetition is not allowed, so that's why, so there's 10 digits you could choose here, except we can't repeat, that's why that one goes back to 9 again. Okay, so yeah, I understand why that one would get a little goofy there on you. Any other questions about this one? We good? Okay. All right, so example 4 says, you have framed pictures of 6 family members. Okay, so you got six separate frames with different people's smiling faces. How many ways can all 6 pictures be arranged? Okay, so you're hanging them on the wall, and you just want to know how many different ways can I put all of these smiling pictures, smiling faces on the wall. Okay, so here we go. This is example 4. So you put the first nail in the wall and you're going to go hang the first picture, wherever it is. How many options do you have for that first picture you're going to hang on the wall? Bless you. There's 6. So now grandma's hanging on the wall, or whoever. Okay. How many options do you have for the next picture you're going to hang on the wall? Okay, 5, right? How many options now that you've hung these 2 on the wall? How many are left? 4. Okay, so we're getting tired of swinging the hammer, so hopefully we're getting close to done. How many options are there for the next picture? 3, and then 2, and then finally you get to that last picture and you finally don't have a choice to make because there's only one picture and there's the last space, 1. So if you have 6 pictures and you just want to hang them all in a straight line and you want to know how many different ways can I do that? Well, it's 6 times 5 times 4 times 3 times 2 times 1. I think that is 720, but because I just know. I did this problem in my office before. Yes. No, there's nothing special there, don't worry. 720. So what this is, when I have a certain number of objects and I want to know how many ways can they be arranged in a certain order, what that is called is a permutation. Okay, and that is the main object of today's lesson. So the definition of a permutation is, and I've written most of it there for you, but just to keep you interested, I left a blank. Okay, so a permutation is, and here are the missing words for you, an ordered arrangement of a given set of objects. And after you're done filling in the blanks, I want you to circle the word ordered. That's the most important word in the definition. Because everything we do today with permutations, we're going to come back and we're going to repeat on Thursday with what's called combinations, which are things that order does not matter. Okay, so what I want you to do as we go through these problems is to make sure you understand what about this problem is indicating that order matters. So when I'm hanging the pictures on the wall, order matters because whoever comes first is hanging first on the wall, whoever's second. So that the order matters because there is a linear arrangement to my hanging the pictures. So the number of permutations, and so you ask, how did you do that so fast? How did you know? Well, the reason I knew this is because, first off, I've been doing this for years and years and years. The number of permutations of n distinct objects is given by, I'm not going to write that whole thing out and bore you watching me, but it's given by this. N with an exclamation point after it. Okay. So that does not mean to say N like real loud, like you're scared, okay, like it's an exclamation. What this is called is a factorial. That's the fancy math word for this. If you've got a scientific calculator of any sort, then you have an exclamation point. If you don't know where it is, I can show you. If you have one of the TI calculators, there's most likely a button that has a PRB on it. It's a probability, and there's 3 things in there, and we're going to use all 3 things over the next 2 classes. And what a factorial is just what we did right here. So, for instance, 6 times 5 times 4 times 3 times 2 times 1, that is 6 factorial. Whatever the number is before the exclamation point, what that means is you start there and you multiply all the successive whole numbers down to 1. So for instance, if we had 8 factorial, 8 factorial is going to start with 8. And then you're going to start with 8 and you're going to multiply times 7 times 6 times 5 times 4 times 3 times 2 times 1. That's what the exclamation means, factorial. So it's just shorthand. Instead of writing all of this down every time, you can just write 8 with the exclamation point. And if you have a calculator that does this, then that's even better. You don't have to put all of this into your calculator. Your calculator will do it for you. So again, before you leave, if you have your calculator with you, you don't know where the exclamation point, where the factorial button is, then let's find that together. Or when you're doing the next problem, if you want me to go over, just wave your hand or wave the calculator. So here's what I would like you to do. Example 5 is very similar to our pictures hanging on the wall. It says 7 books are to be placed on a shelf. How many ways can that be done? Okay, so you can do this problem in one of 2 ways. Okay, the number is small enough because there's only 7 books. So the number is small enough that if you wanted to, you could say, okay, I have 7 options for the first one and 6 for the second and 5 and 4 and 3, and you can write it out. I have no problem with that, but you can also save yourself some time and say, oh, I've got 7 books. I'm ordering all 7 of them. That's just 7 factorial. Okay, either way, I'm not too much of a stickler, but this is the shorthand lingo. And when you pop that into your calculator either way, what is that? How many different arrangements of those 7 books are there? 5,040? Okay, great. Do the next one. Example 6, it says, consider the letters A, B, C, D, and E. How many ways can all 5 letters be arranged? I guess there should be an S on letters, typo. All right, so example 6, I've got 5 letters, A, B, C, D, and E. And so again, if you want to, you could say, okay, I've got 5 letters for the first one and 4 for the second one. Or you can say, okay, I'm ordering all 5 letters. That's 5 factorial, and 5 factorial is 120. Are we doing okay? Good so far? Because now what we're going to do is we're gonna throw in another little twist on this. Example 7 says this. For the previous example, how many arrangements are possible if I'm just going to use 3 of the 5 letters? So how many arrangements are possible if I'm just going to use 3 of the 5 letters? So example 7, well, how many options are there for the first letter? 5. How many are there for the second? So I have I see the frowny face. I have a grab bag. I got my 5 letters, and I'm just going to choose 3 of them out of it. Okay, it doesn't mean that I can see how that misunderstanding happened. I did not mean that we're just limiting ourselves to the A, B, and the C, and how many ways can I arrange those. I have all 5, and I want to just pick 3 of them. Okay, so I've got 5 choices for the first one. I've got 4 choices for the second. I've got 3 choices for the third. Okay, this is letter 1, letter 2, letter 3. And so there are 60 different options. And so this is kind of the factorial. This is when I have 5 items, I'm using all 5. This is when I had 7 items, I'm using all 7. But then how do I do this quickly and cleanly if I have if I have a certain number of objects, but I'm only choosing some subset of those objects. Here, we have 5 letters, we're only choosing 3. Well, I'm glad you asked. There is a permutation formula when you flip the page. It says the number of permutation possible when R objects are selected from a total of N objects. So here, 3 objects are chosen from a group of 5 objects. Okay, here is the permutation formula. Again, if you have any sort of scientific calculator, especially the Texas Instruments one, you have a button that will do this for you. Okay, so this is P stands for permutations. It's the permutations of my total number of objects, and I'm choosing some subset. So I'm just going to make note, N is the total, and then R is my subset. So from my previous example with the letters, the way this would look is it's the permutations of 5 objects, and I'm choosing 3. 5 letters, I'm choosing 3. And the permutation formula looks like this. Well, first off, we know that the number of permutations, if I choose all of the objects, is n factorial. So this right here is what we've already been doing. This is the number of permutations if all objects are used. So from our examples, I hung all the pictures. I used all of the books on the shelf. I used all 5 letters. It was n factorial. But now I'm saying I'm not using all the objects. I'm just using some certain subset. So what we're going to divide by here then is we need to get rid of all the arrangements of the objects I'm not using. So if I'm using R objects, then n minus R is the ones I'm not using. So n minus R is the permutations of the objects not being used. So for instance, for my letter example, the number of permutations of 5 objects, I'm choosing 3. What's wrong?
I don't know if I understand that. Like, so if we're doing, we do 5 minus 3, and then you do like 2 and 1.
Watch. Yes, you got it. You got it. Okay, so this is the number. I've got 5 letters. I'm choosing 3 of them. Okay, and this was a fairly relaxing problem to do without the formula. Yeah, when the numbers are small, you don't necessarily need the formula. But I'm showing you this so that when we do some of our other examples and the numbers are a little larger, when you do need it. Okay, so if I use all 5 letters, then the ordered arrangement of all 5 letters is 5 factorial. We saw that in example 3, I think it was. But then if I'm going to use 3 of the letters, that means how many am I not using? 2, right? Which is 5 minus 3. But that's where that 2 comes from. So if I'm using 3 letters, then I'm not using 5 minus 3 or 2. That's the remainder. So in the top, we have 5 factorial. In the bottom, we have 2 factorial. Now, if you have a calculator, here's my deal with you on the test. If you have a calculator that does permutations, then this is what I want to see from you. Okay? I want to see you write your notation, and then I want to see you set it up. Okay? You don't have to do any calculating from there. Your calculator can do all of the magic. Okay, but I do want to see you set this up. Now, if you don't have a calculator that does factorials, then or doesn't do all this, then what you're going to do is you're gonna roll it out. So 5 factorial is 5 times 4 times 3 times 2 times 1. The bottom 2 factorial is 2 times 1, and then you just do a little canceling. It's always gonna, the denominator, everything in the denominator will always cancel. Okay, there'll be nothing left over. You're not going to end up with a fraction ever. Okay, so if you end up with a fraction when you do one of these problems, check your arithmetic. You did something wrong. Okay, so now 5 times 4 times 3, we already saw that as 60. So you can see the gist of this is being able to set it up. So I've got 3 examples, and I'm going to have you work through them one at a time. So example 8 says this. You are among 9 people forming an astronomy club, because astronomy is awesome. Saturn is really close to the moon right now. So if you're out and you see the moon and there's something bright right by it, that's Saturn. So if that sort of stuff interests you. As a group, you decide to put each person's name in a hat, and you're randomly going to select a president, a vice president, and a secretary, because there's no better way to choose leadership than just to do it randomly. How many different arrangements of officers are possible? Now, I just want to call your attention to the reason order matters. The reason this is a permutation problem is because there's a hierarchy. The first person picked is going to be president. The second one is vice president. So there's a different role for each of the people. So that's why order matters. When we come back on Thursday, we're going to do problems where order doesn't matter. It doesn't matter what order the people get picked in, and we're going to look at why. So here's what I would like you to do. I'd like you to set up this problem. You have 9 objects. You're choosing 3 of them. Yes? Okay, so clear. So what we're going to do first is going to look at calculating the hand. So put in 5. Now go to that. With that. And then you got to look at calculating how many sheets are there. There you go. What I do.
If you're among 9 people, that means you include the 9.
It means there's 9 people total. Okay. Yeah, don't overthink that. You're one of the 9 people. There's 9 total. Well, when you do the problem, be sure to ask the question. And that's why we're here. All right, so example 8. We're in the astronomy club. We're picking our leadership from the 9 people randomly out of a hat. So I want to know how many permutations of how many total people do I have? 9. How many people am I choosing out of the hat? So this is the beginning of the setup. I want to know how many permutations of 9 objects are there when I'm choosing 3 of them. Well, how many permutations are there if I use all 9? Well, all 9 would be 9 factorial. Okay, that's what we started out doing. That's the counting principle right there. 9 times 8 times 7 times 6 times 5, 4, 3, 2, 1. If I'm using all 9, but I'm not using all 9, I'm only using 3. So how many objects am I not using? I know they're people, but I'm just using the word object. Okay, so I'm not using 6. Okay, so 9 minus 3, that's where that 6 comes from. This is the total number of objects minus the ones that I'm using, and that leaves me 6 that I'm not using. At this point, if your calculator does such things, you're good. If your calculator doesn't do such things, then you have 9 factorial divided by 6 factorial, and here's what you do. This is the easiest way I could show you. 9 factorial is 9 times 8 times 7 times then 6 times 5 times 4 times 3 times 2 times 1 is 6 factorial. And the reason I stopped there is now I can cancel the top and the bottom. 6 factorial, boom, see you later. And so 9 times 8 times 7, 9 times 8 is something times 7, what is that? 504? You said you were confused. You sure? All right, well, let's see, because we're going to do another problem. It's going to be pretty much the exact same thing. I'm just changing the numbers. Okay, so example 9 says you're at a skiing event and there's 16 participants. The 5 participants with the fastest times will be listed on a leaderboard. Okay, so that's why order matters. It's a leaderboard, okay, 1st through 5th. So if we were just randomly affixing names on the leaderboard, because that's what you would do, how many different ways are there for 5 names to be listed on the leaderboard? Okay, so this is a permutation problem because I got a leaderboard. So order matters where you are on the leaderboard. How many objects total do I have in this problem? 16. How many of them am I choosing? 5. Great. Okay, so this is the ordered arrangement. So that's why I use P for permutation. Permutation means order of 16 objects. I've got 16 competitors and I'm choosing 5. There's 5 on the leaderboard. Okay, so again, the way to think this through, okay, I'm trying to talk you through this formula so that it's not just a formula, hopefully it makes a little bit of sense. If I wanted to know the ordered arrangements of all 16 objects, what would that be? If I'm using all 16 objects, we're hanging grandma's pictures on the 16 factorial, exclamation point, or just say 16. Yes, there you go. Okay, we got it. But I'm not using all 16, I'm only using 5. So if I'm not using 5, I have to discard how many? 11. I'm using 5, so I'm going to discard 11, more 11s, thank you. So that's 16 minus 5, that's where that comes from. So that's 16 factorial divided by 11 factorial. Again, if you have a calculator that does factorials, or if you've got a calculator that does permutations, you can now plug it in. If you don't, if you just got your 4-function calculator from middle school, then you've got 16 times 15 times 14 times 13 times 12, and then 11, 10, 9, 8, 7, 6, 5, 4, 3, 1 is 11 factorial. And then I can cancel, and then it's just a matter of multiplying those numbers together. And how much is that? 524, 116? 60. All right, one more. So if you got a question, is it better?
Yeah.
Okay, we do it. No?
So does that mean that there are over 500,000 ways to list 5 people's names?
Out of 16, yes. If you have 16, you have a group of 16 and you want to just pick 5, there's 524,160 ordered arrangements. Yes, unique ordered arrangements. That would be quite the tree diagram, wouldn't it?
I thought we only have about 5 people. So if it's just 5, then why is it that many? Because there's like 5 people in this room, so we could like, it doesn't take that many to put us in order of 5.
Well, we're talking about how many different orders are there. So for instance, let's go back to our A, B, C, D, E example. Okay, so we have A, B, C, D, E. And we're picking 3 letters. We want to know how many ordered arrangement of the 3 letters are there. Well, okay, so that means there's A, B, C, but then B, A, C is different because it's a different order, right? C, A, B would be different than that. A, C, B, like these are all the ordered arrangements of just those ones. I haven't even talked about the D and the E yet. So there's 60 different, we found out when I'm picking just 3, there are 60 different ways to do that. Okay, because there's particular orders. So if I'm choosing 5 people out of 16, okay, then there's Steve and Bob and Chuck and John, and for some reason I can't even think of names right now. That's okay. And Paul and Jerry, there you go. But I thought of Paul first. Okay, so these are the 5, but now, so these are 5 out of 16, but there's all different ways I can order those 5 that I have to think about. And then Jerry, okay, so maybe we replace John with Jerry, and now we have a whole new group that we can find all the different orders. And that's why it builds up to be 524,000 different ways to do that. You guess?
Whatever you say.
Oh, okay. You're just gonna
I'm just gonna go with it.
math by faith. I see. That's good.
It's kind of like the tree. If I overthink it, I'm just not gonna get it, so I'm just gonna accept it.
Okay. Well, I mean, maybe it'll make more sense after you do a few more problems as you see some different examples. Try example 10. It says there's a bike club. There's 10 different routes that its members want to try. There are 6 days to fill for the trips. So order matters because what trail you do on what day is going to matter. So there are 6 dates to fill. How many ways can the different routes be assigned to the available dates?
What would the problem look like before it goes?
It's gonna be a great question. We'll talk about that.
Oh, that's not, what am I?
No, it's a great question. The difference is situations where order doesn't matter is where you're picking things for a group, but there's no hierarchy. So instead of picking, for instance, instead of picking a president, a vice president, a secretary, you're picking 3 people to be on a committee. Okay, and there's no hierarchy on a committee. Everybody's the same. So order would not matter. If you get picked first or you pick third, you're on the committee. Okay, on this one, it's permutations, it's orders, because I'm picking places to go on different dates. How many objects do I have total to choose from? 10. There's 10 trails that we want to go to. Okay, and how many of those trails am I going to pick? 6. Okay, and so order matters because the trail that's where we're like Ocala. Okay, well, what day are we going to do it? We could do it on the first day or the second up through the 6th. So that's where the order matters. That's why there's all these different arrangements. So if I was picking all 10 trails, the total number of ordered arrangements of all 10 trails would be 10 factorial. Okay, but we're not using all 10. We're only using 6. So that means how many am I not using? 4. Okay, 4, which is where the 10 minus 6 comes from. Okay, that's 4. And so we've got 10 factorial divided by 4 factorial. Again, if your calculator does this, that's good. If not, then you've got to do a little multiplication. And your multiplication is 10 times 9 times 8 times 7 is 65. And what is that when you multiply that out?
151,200.
So there's that many ordered arrangements. Now, to your question, to maybe make it, let's say we didn't care what dates we went. We just want to pick 6 trails to ride. So order doesn't matter. That will be what we talked about on Thursday. That's going to lessen the number. But the number increases because we're thinking about order in particular. Okay, so it matters what date I go on what trail ride here. Okay, so it's not just I'm going to Ocala, I don't care when I go. It's I'm going to Ocala on Thursday or I'm going to Ocala on Monday. And so that's why there's a lot of arrangements because the order is particular. Okay. All right, so we've got 2 more examples here. Example 11, example 12. And what is particular about these is if you remember our example on the previous page, A, B, C, D, E, we had 5 letters that we wanted to arrange, but all 5 letters were different. Okay, so there was no repetition of letters. So for example, in example 11, what I want to do is I want to arrange the letters in the word Cincinnati, which I don't know that I can spell. There we go. But here's the thing, here's the issue and why this is our second to last problem. I've got repeated letters. Okay, so how many distinct letters would there be for my first? So that becomes the issue. So when you have, when you want to do ordered arrangements, with repeated objects, here's what you do. So I want to know how many ways can I rearrange, can I jumble up the letters in the word Cincinnati? Okay, we're going to use all the letters. It's much more complicated if I was just going to pick 3, so we're not going to worry about that situation. So for this last thing, when we're dealing with repeated objects, we're going to say we are using all of them. And so here's how we do it. If they were all unique objects, or if they're all unique objects, I have 1, 2, 3, 4, 5, 6, 7, 8, 9, I have 10 letters in Cincinnati. So if they were all unique, okay, then there would be 10 factorial ways to arrange them. Okay, 10 times 9 times 8 times 7. Okay, but if I pick the C first, doesn't matter if it's this C or that C. So what that does is it reduces the number of arrangements. So what you do then is anything that's repeated, we put in the denominator. So for instance, how many C's do I have? I have one C, I have two C's. So what we're gonna do is we're gonna divide by 2 factorial. I'm just gonna make a little note here, that's for the C's. What other letter is repeated in Cincinnati? I, how many I's do we have? Okay, we got 1, 2, 3, you're 100% correct. So I'm gonna divide by 3 factorial down here, and that's for the I's. What else is repeated? N's, I got 1, 2, 3 of those. So 3 factorial, that's for my N's. And then is anything else, that just leaves that A and that T, so those are not repeated at all. And so this is how you figure out the unique ordered arrangements when you have things that are repeated, when you have multiple of the same object. And so this now, calculator probably doesn't have a button for this, but if you have a factorial button, then you can use it and do some division. Otherwise, what I'm going to do is I'm going to do 10 times 9 times 8 times 7 times 6 times 5 times 4 times 3, 2, 1 is 3 factorial. 2 factorial is 2 times 1. This 3 factorial is going to be 3 times 2 times 1. And then I'm going to leave that last 3 factorial as 3 factorial just to cancel it. And then everything should cancel. Again, you should never end up with a fraction here when you do this. So I'm going to cancel this 3 factorial with that 3 factorial. 3 times 2 here is 6. So I'm going to cancel this 6 with this 3 times 2. And then 2 goes into 10, 2 goes into 10 5 times. So then I've got 5 times 9 times 8 times 7 times 5 times 4. I have no idea what that is. So I've got 5 times 9 times 8 times 7 times 5 times 4, and that's 50,400 ways that I can arrange the letters in Cincinnati.
Wait, why didn't you put the other one in like why did you just leave it in factorial?
I just left this 3 factorial here because at the end of 10 factorial, 3 times 2 times 1 was 3 factorial. So you could have written it out. I was just being lazy. So I could have written out 3 times 2 times 1 and 3 times 2 times 1 and just canceled. Yes.
So what about the A and the T?
Well, since there's just one, that we don't have to worry about that. You only have to divide by things that have been, because this is the 3 ends, the ordered arrangement of the 3 ends, but all the ends look the same. So it doesn't matter if one ends first or second or third, it's all N. What last part? The no? Okay, so 10 factorial. The exclamation point means I multiply my whole numbers all the way down to 1. So 10 factorial is 10 times 9 times 8 times 7 times 6 times 5 times 4. Now what I chose to do is because I see I have a 3 factorial, I said 3 times 2 times 1 is 3 factorial here. If you don't, if you're uncomfortable doing that, then you can just keep going. 3 times 2 times 1. Okay, it doesn't matter. Then in the bottom, 2 factorial is 2 times 1. 3 factorial is 3 times 2 times 1. That's what the exclamation point means, is I multiply each number starting with this down to 1. So 3 factorial is 3 times 2 times 1. And now I just cancel. Okay, a factor in the top, factor in the bottom. So I've got a 2 in the bottom, I've got a 2 in the top, goodbye. I've got a 3 in the bottom, a 3 in the top, goodbye. 3 times 2 gives me 6. So 6 in the bottom, 6 in the top, goodbye. And then 2 in the bottom, and then I'm just going to cancel the 2 with one of these even numbers. So I just did 10 because it's right over the 2. You could have done the 8 or the 4. 2 goes into 2 once, 2 goes into 10 5 times. And then multiply 5 times 9 times 8 times 7 times 5 times 4, and we got 50,400. Because what's 1 times anything? And then when you divide by 1, it doesn't, like 8 divided by 1 is just 8. So the ones don't affect the arithmetic. On the calculator, I would put in my calculator 10 factorial and hit equals. and then hit the divide button, 2 factorial, and then equals, then divide by 3 factorial equals. All right, so last problem, example 12. How many different ways can you arrange the letters in the word Mississippi? You don't have to cancel out the 1 because the 7 divided by 1 is 7. Okay, so if you have 7 of something and you're dividing it into one group, then that one group has 7 objects in it. Okay, so finishing up, how many ways can I order the letters in Mississippi? Well, first I have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11 letters. So that's 11 factorial if all the letters were different in Mississippi, but they're not all different. I've got S's. I've got 1, 2, 3, 4 S's. So I've got 4 factorial here. I'm just going to write that's for my S's. And then I've got I's. So I've got 1, 2, 3, 4 I's. So another 4 factorial. That's for the I's. And then we've got these 2 P's right here. So divide by 2 factorial. And then we've got 1 M. That's not going to affect anything. And there we go. We good so far? And so then I've got to simplify this. So again, if my calculator does not have a factorial, again, I have calculators you can borrow, but when you're doing your homework, Dollar Tree has a scientific calculator. It has a factorial on it. It's $1, so it will save you a little time on your homework. So here we go. 11 factorial is 11 times 10 times 9 times 8 times 7 times 6 times 5 times 4 times 3 times 2 times 1. Woo! 4 factorial. 4 times 3 times 2 times 1. 4 factorial. And then 2 factorial. And now it's just a cancel party. Okay, so this 4, 3, 2, 1, I'm going to cancel with this 4, 3, 2, 1. Let's see. 4 times 2. Well, let's do this one at a time. 4 goes into 8 twice. 3 goes into 6 twice. 2 is going to cancel with one of those 2's that's left over, so I'm going to cancel with that one. And then this 2, I'm going to cancel with that other 2. Okay. There's other ways you can cancel, okay, but we all should end up with the same value at the end, okay, because you could have divided one of the 2's into 10. It doesn't matter. But I have 11 times 10 times 9 times 7, and so that is going to turn out to be something. I'm sorry? And don't forget the 5. Exactly. I was about to forget the 5. But thankfully, you guys are more astute than I am. So I've got 11 times 10 times 9 times 7 times 5, and that is 34,650. All right, and that is the counting principle and permutations. Woohoo!